Swayam Prabha. Digital India. Educated India.
If I prove this, then I will be done with the proof that in fact maximum matching is equal to minimum vertex cover, right. So, let us view this picture again slightly more clearly. So, there is this S, there is this non-S part, T is here, S is here, and what we have argued is that all the matched edges are sitting here. I will draw one representative, and all these vertices are matched and all these vertices are matched, and I have picked exactly these partitions. So, I will call my set VC is equal to X minus S union Y intersection S. I want to claim that this is a vertex cover of the graph. If I want to prove this, what should I prove? All the edges have been covered. That is something that we have not shown, right. So, we need to argue that all the edges will get covered if you pick just this collection of vertices. We have already argued that this collection of vertices is equal to the size of the maximum matching. So, we have not picked more number of vertices. We can never pick fewer number of vertices because for every matched edge you must pick one endpoint. Okay, so then which edges are the ones which are at a risk of not getting covered? So, these edges, right, these edges are worrisome edges because nobody covers them. So, what is the argument now? But these need not be matched edges, these could be unmatched edges, right. So, okay, let us first ask, can both the endpoints be unmatched of such edges? So, let us take an edge, particular edge, and let us say both the endpoints of that edge are unmatched with respect to the maximum matching. If that happens, what do you there can be unmatched vertices on these two sides, right, that is what we have argued. Let us say that there is a edge which is both the endpoints are unmatched, then it is the matching is not maximum or the flow is not a max flow because there is an ST path actually, right. So, that this cannot happen. So, what is the direction of these edges? All are unmatched edges. So, the direction of these edges is, it has been unchanged, that it is forward, right. And why were these vertices in S? This is all the set of vertices which are in S. So, if there were edges of this type which are forward edges, you have already reached this vertex using S, you could have extended that path and extended it to reach this vertex. But you put this vertex in a non-S partition, which means that there was no path by which you could have reached these vertices starting at the vertex little s. Remember that these edges are unmatched edges, therefore they have a direction which is forward. You have already reached one of the endpoints of this edge, and the other endpoint is also reachable via the same edge by taking the forward edge, and therefore your partition, that is this vertex belongs to a non-S side, is incorrect, right. Therefore, there exist no such edges in the graph, right. So, all these edges in fact are absent. In fact, that is also an argument why there cannot be matched edges of that type. Actually no, I will correct myself because matched edges will have their reverse direction. So, we will still have to use the old argument, but unmatched edges of that kind cannot be present, right. So, all the edges, matched edges are never of this type because they always lie either in the S part or in the non-S part. Unmatched edges can never cross in the form that S intersection X to Y minus S, there cannot be any such edges. Can there be unmatched edges of this kind? Can there be unmatched edges from this part, that is X minus S to Y intersection S? There is a difference between an unmatched vertex and an unmatched edge. All the vertices here are matched, all the vertices here are matched, but between two matched vertices there can be an unmatched edge, right. So, let us go back to this example. So, so we are asking whether there is an edge from the non-S part on the X side to the Y intersection. So the non-S part, which is this, to the y side, this is A2, and to the, yeah, so in this example there isn't, but there can be edges, actually there is, right? So this, I'm sorry, this A2B1 edge I have not drawn. So this A2B1 edge was there in the bipartite graph. I did not draw it in the residual network. So A2B1 edge in fact is present, and this edge is a witness for such edges which can be present from x intersection S to y, x minus S to y intersection S. But the presence of such edges doesn't hurt us, because already we have chosen x minus S and y intersection S to be our vertex cover, and these actually both the endpoints are present in the vertex cover. Therefore we are safe. In fact, we could choose this, and we have argued that all the edges that are present in the graph are having the property that either one or both of its endpoints get covered by this set. So to recap, what we have shown is that we have selected a set VC of size which is equal to maximum matching size, and the set covers all vertices or all edges in the graph, in the bipartite graph. Therefore it is indeed a valid vertex cover for that graph. So this proves that in fact the size of the maximum matching is equal to the size of the minimum vertex cover in the graph, and this completes the another proof of the Koenig's theorem, right? So we use network flows to reprove the result, that is the Koenig's theorem here. He claims that I did not prove that it is a minimum vertex cover, I just proved that it is some vertex cover. So let us see what all did we prove, okay. So we proved that this set VC that we constructed is a vertex cover. So what did we show? The size of the VC, the number of vertices, is exactly equal to the size of the matching that we had, which is exactly equal to, actually which was a maximum matching M star, right. We had picked a maximum matching, and then we constructed the residual network. And what do we know about any vertex cover and any matching? So if I show you some number of matched edges in any graph, and I ask you what should be the size of the vertex cover in that graph. So size of the matching is exactly equal to the number of edges, so you don't have to divide it by 2. So I must pick, so any vertex cover must have size which is greater than or equal to the size of any matching, right. And now what we have done is we have shown a vertex cover which is exactly equal to the size of the maximum matching. So in fact, if you show a vertex cover which is equal to the size of any matching, then it suffices, right. So does everybody see that we don't need to explicitly prove, we have actually given a proof that it is both a vertex cover and a maximum, and it is a minimum vertex cover. Okay. So in the remaining part that I have, I'll have time for just doing one more reduction, and we'll do this. We'll see another problem which has come up in slightly different flavors. We'll call this the problem of edge disjoint paths in a directed network or directed graph. So let me state what is the input to our problem. The input to our problem is a directed graph GVE, and we are given a designated pair of vertices S and T, and our interest is in computing paths from S to T which have this property that they are edge disjoint, right. So the graph need not be bipartite anymore. Yeah, so maybe this is our network. So what are, let's ask what are edge disjoint paths? What do we understand? So one path from S to T is SA1, A2, A3, T. Another edge disjoint path could be S, A4, A2, A5 and T, right? I cannot go to A3 because if I go to A3 then I should use the edge A3T. Such a path would not be edge disjoint. They can be vertex intersecting, like these two paths are vertex intersecting, but they need to be edge disjoint, right? So these are two paths which are edge disjoint from S to T, and our goal is to compute a largest possible collection of such paths, right? So we are given a directed graph or a directed network. We are also given the two vertices S and T, and we are interested in computing these edge disjoint paths, right? Okay, so again we are not going to invent an algorithm from scratch. We are going to use possibly a reduction to network flow. So in this case the setup seems to be much nearer to the network flow setup, where we already have a directed graph, we already have an S and T, and then the only thing that is lacking is capacities, right? So we need to find out capacities and assign them possibly if we want to use network flows to solve this problem. So again our setting will be that we are given GVE, we are given this ST, we would want to come up with a flow network D and a pair ST such that the max flow in this flow network corresponds to the number of edge disjoint paths in G and vice versa. That is, if you have k edge disjoint paths in G, you must be able to show a max flow of value k in the in the flow network D. So can we have some suggestions for what kind of a flow network do we want to set up? So most of the things are there in ready for us, that is we have a directed graph here, and the flow network also requires us to have a directed network. The S and T are also given to us, maybe we can make use of them, and we need to set up the capacities appropriately. So is there a natural choice for the capacities? So we try to set every edge a capacity of 1, right? So I will set up this flow network where every edge has been given a capacity of 1. We find a max flow using some flow algorithm, and we would like to argue that the value of the flow in D is exactly equal to the number of edge disjoint paths in G and vice versa, right? So the setup of the flow network is clear. We will keep the S and T the same, and we will just assign unit capacities. Okay, so let us do the simpler direction first again, that is, suppose we had k edge disjoint paths from S to T in G. I would want to show a flow of value k in this flow network. Yeah, so take every path in this collection of paths, set the flow value on all such edges on these paths equal to 1, and for all other edges in the network which do not belong to these paths, set the flow value equal to 0, right? So so what do we need to argue to show that this is a valid flow? Conservation, right? So capacity constraints are met because anyway we set 0, 1 values. There is conservation. So what allows us to argue for conservation? So if you look at any arbitrary vertex, yeah, so can there be multiple edge disjoint paths using this? So pick up an arbitrary vertex u in your graph, which will also be there in the flow network. Can there be multiple edge disjoint paths which contain this vertex u? There can be, right? But for every such path there will be an incoming edge and there will be an outgoing edge, and therefore you will actually have exactly as many. So if there are some k prime number of paths that use the vertex u in this collection, then there will be exactly k prime incoming edges to this vertex u and k prime outgoing edges to from this vertex u, which will account for the inflow equal to outflow for every vertex, and that is true for every vertex other than S and T, and we have ensured that flow conservation is there. What about the value of the flow? The value of the flow is defined as the the sum of the flow which goes out of S minus the sum of the flow that comes into S. Since these are edge disjoint paths from S to T, we know that there must be exactly k outgoing edges for which we had set a flow value equal to 1, and again the value of the flow must be exactly equal to k. So if you pick up any collection of k edge disjoint paths here, you will be able to find a flow value which is exactly equal to k, and it is a valid flow in the flow network that you have set up. And therefore, if you consider a max collection of edge disjoint paths, again you will get some flow here. So we should now ask the reverse direction, that is, if somebody gives us a max flow or any flow in the flow network D that we have constructed, we should be able to get back a collection of edge disjoint paths. So again I will state the claim: if D has a flow f of value k, then there exists k edge disjoint in G. So where do you expect these edge disjoint paths to reside once somebody has given you a flow? So what do I mean by somebody has given us a flow? We have been provided with the flow function, that is, on what edges is the flow non-zero and on what edges is the flow 0. And we will assume that the flow is integral and therefore it is either 0 or 1. And it cannot be anything other than that because of the capacities. So where do you expect the edge disjoint paths to reside? So okay, so what you are claiming is you just blindly take all the edges that have flow 1 and you will claim that they form k edge disjoint paths. This is what is your claim. Okay, so my argument is, why can't such a thing happen? So I go from S to A1, then to A2, then to A3, then come back to A1, and then go back out of this thing to A4 and do something like this. This is a valid flow for me, right? So all these edges have 1 unit of flow. You see the way, right? S, A1, A2, A3, A1, A4, A5, T. Such a flow is a valid flow in the flow network, and a flow algorithm is okay to give me such a flow as an output. And I must be able to say that I can still extract out and show you k edge disjoint paths. So I cannot immediately look at all the edges which have flow non-zero and claim that just output them and they will be the k edge disjoint paths. So there is a little more to this. Outgoing edges. Okay.
And the moment at a vertex where two paths possibly merge into one path, which will lead to the edges being the same for those two paths. Like if we have two paths and let's assume that they are not edge disjoint, so they must share at least one common edge.
Okay, so just this thing. So this is not an example where the paths are not edge disjoint, but they are actually not. This is not a simple path, right? So yeah, okay, go ahead.
We want to prove that there have to be k edge disjoint paths.
Yes.
So the first point is, starting from the source, we need to have k outgoing edges.
Correct.
Which will be part of the paths. And if at all any of these paths merge, then any of these paths get a common edge.
Common edge. Okay, but actually what one can claim is that the collection of vertices that you have, okay, so you look at a subgraph of the original graph and you have obtained it from your flow network such that the flow network, on all those edges of the flow network you have non-zero flow or unit flow, right? And because flow is conserved, you must have the condition that for every non-ST vertex you must have incoming edges is equal to outgoing edges. And this is true even in this example. So I agree with you that you cannot have that, you'll have fewer incoming edges and larger outgoing edges and so on, right, because flow is conserved. Yes, okay, so maybe I should also say that we are looking for simple paths from S to T, right? And what we still need to argue is that we can extract out simple paths and show k simple paths that are present in the, or that are present from S to T given the max flow, right? So here the path that I have shown is edge disjoint, but it is not a simple path, right? And still we have this problem that we need to extract out these k simple edge disjoint paths. So you are right that you cannot have that the flow is not conserved because we have gotten it from the. Okay, so one way is to try to greedily extract these paths and exhibit actually these simple paths from S to T, right? So collect these, try to get these paths, and the only reason why you could get into difficulty is because you complete a cycle in between, right? So you start, so clearly there must be, as you have pointed out, there must be k edges out of S. You take any edge which is going out of S. If you reach a vertex A1, there must be an outgoing edge from A1 again carrying unit flow and so on. And the only reason you can get stuck is possibly you go back to the same vertex that you had visited, right? So we want to show that although this happens, we do not have too much trouble. There is still a simple path from S to T, which is this path, which is S, A1, A4, A5 and T, which we can extract, and we want to show systematically how to extract these paths and give out actually those k edge disjoint paths. So this is what we are going to try to do. So what we will say is, if our flow network returns a flow function f at the end of the algorithm, then whatever edges carry unit flow, there are k edge disjoint paths which are contained inside those edges. So we had a flow network D where we had the vertex set V prime and the edge set E prime. Let me say that there is a subset of the edge set E double prime which are such edges such that f of E is equal to 1. I have collected all those edges. I claim that since f is a 0, 1 flow in the flow network D, then there exists a set of k edge disjoint paths in the set E prime. So what I am saying is E prime itself may not be the set of k edge disjoint paths, but the k edge disjoint paths are contained inside this set, right? As this example also shows that I can possibly throw away some edges and still construct a collection of paths which will be edge disjoint. So is the claim clear? Okay. Okay. So what we will do is we will do an induction on the number of edges that carry unit flow in this set E double prime, right? So we are going to prove this by induction on number of edges that carry unit flow. Okay, so let me state my claim again, that if I have a flow f of value cardinality of f, then there exist those many, that is cardinality of f many edge disjoint paths in this collection E double prime. This is what I want to prove, and I want to prove this by induction on the number of edges that carry unit flow, right? So if I did not have any, so the base case I will take a very simple thing, that if I did not have any flow, that is there were 0 edges that carry unit flow, then I have nothing to show, and therefore the base case is established, right? So now what I will do is, if I have a non-zero flow, I will do the same technique that I was doing earlier, that is I will start from S and start extracting this path. If I am lucky enough and if I reach T, I will I have actually found out one edge disjoint path, and what I will do is I will take this edge disjoint path, reduce the flow on all the edges of this edge disjoint path by 1, and therefore the flow value will also decrease by 1, and therefore if my initial flow value was cardinality of f, I have a new flow f prime which has value which is cardinality of f minus 1, or value of f has gone down by exactly 1. But I have also reduced the number of edges that are carrying unit flow, because I have actually deleted at least one edge, and or maybe possibly more, and therefore now I can apply my induction hypothesis. If I have a flow f prime with so many with value this and fewer number of edges that are carrying unit flow, then I apply my induction hypothesis, and therefore I have f prime many edge disjoint paths from S to T plus the one path that I have extracted. Therefore, I complete my argument in this case. The thing that remains is our case where we end up, before we reach T, in fact we do not reach T, but we actually loop back and we find a cycle, in which case now the induction step has been set up, or the induction has been set up properly. And how will you use this induction now? So suppose we find this cycle, what should we do? By removing the cycle, what do you mean? Yeah, don't delete the edges, but reduce the flow on all these edges on all the edges of the cycle by 1. Note that this is going to be still a valid flow. Why? Because for every edge you have reduced the incoming flow by 1 and the outgoing flow by 1. So flow is conserved. Have you actually reduced the value of the flow? You may reduce, you may be worried if this cycle contains S. If this cycle doesn't contain S, you have not reduced the flow, because the value of the flow is still the number of edges that carry unit flow outgoing from S, that has not changed. Even if it contains the source vertex S, you know that the value of the flow was exactly equal to the number of edges that go out of S which carry unit flow minus the number of edges that come into S that carry unit flow. Therefore, in either case you had one going, one in the addition and one in the subtraction. So you must not have reduced the value of the flow, right? But what you have reduced is the number of edges that carry unit flow for sure, because you have found a non-trivial cycle, and now you apply the induction hypothesis again, right? And once you do this, you see that you have you now don't go to, you go to a different flow f prime, but the value of the flow remains the same, and now by induction hypothesis you still have f cardinality of f prime which is equal to cardinality of f many edge disjoint paths from S to T. Okay, so in the last 5 minutes I'll just try to do the same thing for undirected graphs. So remember, we asked our question on directed graphs, that is we are given a directed graph and a pair of vertices S and T, and we would like to ask, we would like to find the number of edge disjoint paths from S to T. We said that it is exactly equal to the max flow in a unit capacity network obtained by that. If the same question was given in undirected graphs, the same question is valid. How do you convert that undirected graph to a directed flow network? So this same question we are asking in undirected graphs now. So we have the same setting, we have an undirected graph, a pair S and T, and we want to find the maximum number of edge disjoint paths from S to T, but these paths are now going to be undirected paths. Yeah, any ideas how to convert this network or the undirected graph to a directed flow network? You want to save yourself from that anti-parallel edges, right? Okay, good. Okay, so yeah, so what he suggests is, and he has taken into consideration the first restriction that we put is that the flow network should not have anti-parallel edges. So if you had an edge UV in the undirected graph, he is adding the edge UV in the directed graph, and then maybe he will add a dummy vertex, we will call it DUV, and he will add these two edges again. What should be the capacities of such edges? Same. So all of them will give unit capacity, right? Actually, so this is a correct thing, but just for the sake of presentation, this you can do for the flow network itself, right? So you are right. We will just say that we have these parallel edges, right? Because anyway for the flow network you will do this. just it will make the exposition slightly simpler. So good, you have converted your flow network you have converted your undirected graph into a directed flow network. You again have S and T, you compute the max flow, right? And now of course you will have those dummy vertices, you will again, whenever you get flow, you will merge them, and finally you will get back something on your directed network that you have constructed, and then you want to get it back to the undirected network, right? So now do you see any issue with this? So we have already established the correctness for the directed setting. So whatever paths that you get in the flow network can be correctly converted into k edge disjoint paths in the directed network. But what if some path uses the edge uv and some path uses the edge vu, which I mean of course would have been split earlier but then finally again merged. So in that, when you bring it back to the undirected setting, it is the same edge, right? And you have lost the or you have violated the restriction that they should be edge disjoint. In the directed setting they are edge disjoint, but in the undirected setting they no longer remain to be edge disjoint. So I hope everybody sees the issue, right? We have a small issue that we are almost there, but some paths may use the edge uv in the forward direction. Some, actually there can be at most one path because these are edge disjoint in the directed setting, and there can be a path which uses vu in that direction, but when we make them undirected paths they use the same edge uv. So let us ask again, can we modify our flow such that the flow doesn't have such a bad thing for us to happen? So my claim is that in your flow network you must have that uv also carries 1 unit of flow and vu also carries 1 unit of flow. That is the only reason why you must have landed up in a situation where you have extracted paths where a path uses uv in the forward direction and the vu edge. And so can you modify your flow? So what if I change such flow into another flow f prime, where f prime of uv is equal to f prime of vu is equal to 0, because I just set the flow along these two edges as 0, I keep the remaining flow as it is, will it change the value of the flow? Again, even if it were S, it will not change the value of the flow because there is one outgoing edge, one incoming edge that I have. So the value of the flow will remain unchanged. For every other place, the value of the flow doesn't change. Will it violate flow conservation? Because again, at U you have reduced, I mean you have reduced one, and you have reduced one from the incoming and one from the outgoing. Similarly at V you have done the same thing, right? So what one can do is you can simply modify the flow such that it does not have these bad cycles, and so either it could be the case that only one of them, UV or VU, carries the flow, in which case you would leave it untouched. If both of them carry the flow, then you simply modify the flow to get another flow where this thing does not happen, both the edges do not have the flow, and then you simply apply your edge disjoint paths on directed graphs. Now you are guaranteed that whatever paths you get will also be edge disjoint paths in the undirected setting, right? In fact, you can do a slightly more general thing in general flow networks. If you have two edges which are anti-parallel edges, that is AB and BA, and both of them carry non-zero flow, then you can take the one which carries smaller of the two flows and subtract them from the larger, and it will not change the value of the flow, neither the flow conservation, and at most one of them will continue to carry flow in the flow network, right? So what we have done is the same kind of algorithm can also be applied to undirected graphs with a small modification here, and therefore we get maximum number of edge disjoint paths even in undirected graphs. So let me quickly summarize what all we have done. In the morning, Professor Nari started with the definition of network flows. We saw the definition of a residual network, then the Ford-Fulkerson template algorithm, and we saw the max flow min cut theorem. This was in the first lecture. In the second lecture we we revisited again this residual network construction, and we asked what if we actually did a simplistic idea of just reducing the capacity of every edge and not adding these reverse edges, would it work? And we saw that the addition of these residual edges was very crucial to the correctness of the Ford-Fulkerson method, and therefore these reverse edges are in fact very crucial. So we saw the need for reverse edges. Then we also visited what is the complexity of the Ford-Fulkerson method under the assumption that the capacities are integers, and we saw that the complexity involves a term which has the max capacity on any edge, which is not which need not, therefore the running time of the algorithm need not be polynomial in the size of the input. Then we looked at a reduction to the bipartite matching problem. Sorry, the bipartite matching reduces to network flows. Okay, so we did not use this term, to network flows. And we established the correctness of this reduction. And in this class, we have looked at the Koenig's theorem, which proves that if a graph is bipartite, then the maximum matching size is equal to minimum vertex cover. And then we looked at a different problem, which is edge disjoint paths. In both directed and undirected networks. And all these two classes that I have presented, most of the material is from Kleinberg and Tardosh, and you can look at the book if you have any questions about it. So thank you very much.